personal laptops and so on. This is primarily going to be about sort of a postmortem. Usually people tell you about what their successes are. There's often much more to be learned about when things go wrong. And I guess I was reading something today which was really important to take away. You know, it's what you don't know that ultimately often gets you. And as you'll see, what I talked about last night was one of the things I didn't understand along the way. I didn't know it. And I didn't know it until last fall, even though much of our mesh networking stuff had long since gone down in flames. So, as you all know, I'll spare you this. We built a machine. It shipped in some number of millions, 3, 4, 5 million. I don't know what the number is. It's helping a lot of kids. And the networking piece of the vision was that children can just sit down under a tree, no infrastructure, no nothing, and collaborate with each other. Okay? We also wanted to be able to easily spread the network around in a village in a serious way. And toward this end, the vision was that each OLPC, even when the laptop might be suspended, would leave the radio piece of it on and running all the time, 24/7, or at least daytime hours and into the evening, so that the whole village might have connectivity, probably back via the school. That was the intent. So what was implemented is some early version of 802.11s draft for a self-configuring mesh. And the other idea was, well, we can take the same modules and package them differently, mail them to a tree, whatever. If you want to use your laptop in a place where you don't have good line of sight, then you put one of those someplace, and so on. And this is in Arahuac, Peru. This is, I think, one of the networks that people possibly in this room built in Athens. There's another very similar pole up here, as we know, or tower up here with interesting stuff with the usual sort of mesh thing. And the intent was to, okay, we'll have a server in the school, and from there, some backhaul to the rest of the internet. And we might have a bunch of nearby schools that we would then network together, or mesh of meshes, if you will. There's the vision. A little more detail. This is what is in the OLPC, which is a little wireless module made by Marvell, which has an ARM processor with an order of megabyte of RAM. And for at least the 1.0 version of the OLPC, the only interface that the modules shared, or the chip shared, the SoC shared with what we had in the OLPC was USB. Boy, do I hate USB, particularly for networking. And it indeed can be left powered on. The OLPC is suspended to continue forwarding packets. Unfortunately, the firmware is closed. We were able to actually work with the implementers of at least the mesh firmware. We had other interesting things about the piece of the stuff that talking to boot the device, the smart module. That being closed made things debugging many times harder. So some of these got built. I don't know how many they've been deployed. This is just a nice green thing that would have one of these modules in it and hang it for whatever you like, or nail it to the tree. I've seen many similar devices around here. So first I want to say this was not a complete failure by any means. You could take 3 or 4 or 5 or 6 or 10 OLPCs underneath the tree, open them up, and some of the people might wander off. Everything works just as you might like. And a child can and does do it. It really does, can fully auto-configure and the right thing happen without any manual configuration. What went down in flames? Well, the dense mesh. The problem is, what happens when the kids arrive at school in the morning? Okay? All of a sudden, you have these computers, and they get turned on. The wireless modules may or may not have been running in the meanwhile. You can all hear each other. You might have a school of 30 kids, 50 kids, 500 kids. When I say dense, I mean dense. And some decent fraction of the radios to be able to hear each other. So the dense mesh doesn't work, and I'll try to explain what went wrong. And it's quite spectacular. It's one of the two major problems we had, and I didn't understand the second until last summer and fall. And making this all happen in terms of scaling, this never happened at the thing up. So what are the problems we had? Well, I first want to touch on power, because some of you may know there isn't an electric socket every place you want to go, particularly when you want to put your devices all over the place to fill in holes. There's scaling issues, and I'll come back to those multiple times. And then there's this presumption that many of us have had, which I've been disabused of, that, oh, well, 802.11 networking looks a lot like Ethernet, so things that work on Ethernet should just work. And then one step further removed is the presumption that will work on a mesh of those things. Then there's sloppiness. We were guilty of some very sloppiness. And then, off of what itself. Power problems. Well, we were told what we should expect for the module to consume in terms of power. When we started out, it never got even within a factor of 2 of what was claimed. The net result is, given that there's only so much battery in the laptops, that power being a scarce resource when the kids go home at night, actually maybe a scarce resource even when they're at school, but that's a different, more generic, what do you learn about reality of what electric power availability is in the world. I don't want to spend our time here today about that. Meant that there's too high an incentive to want to really power things off, because the batteries would run down. Okay? So later versions of this device may do a lot better in terms of power. They were supposedly going to, but I haven't actually checked into it whether they do. And since I've not been working on the project for a couple of years now, I don't know. To some extent, there's been a saving grace, which some of you are probably aware of, which is you can get a 5-watt solar panel that's about this big, and they're reasonably cheap, like $15 now. At least they were there several years ago.
So what type of, or kind of, how much power is being drawn by that wireless module?
Oh God, it's buried in laptop.org. The actual power measurements for everything in OLPC are on the laptop.org website. I don't remember what the numbers were, but it was
half a watt.
A watt or half a watt. Yeah, it's just, and the problem is when you've got a 22 watt-hour battery, how many hours do you go before you drain your battery? So I will say at least that in certain climates, maybe in this one here, you get a lot of sun a lot of the year, and the solar panels have gotten cheap enough that you can sort of survive to some extent, but not. Okay, so many of the scars on my back are from scaling. Actually true throughout my career, but be that as it may. You can make lots of things work at small scale of a few or 5 or maybe 10. As you all know from deploying networks of thousands, it gets a lot harder as you scale up. So what was implemented for the mesh stuff in the draft standard, at least, I don't know what their later documents look like, just plain doesn't scale. It's n squared, depending on the n where n can hear each other. Okay, so it doesn't take very large n for you to have a real problem. And that's in the routing in the mesh. So first thing you do when you emit a packet is that the mesh starts talking to itself to find a route. So at least at the time, and they said I haven't been keeping track of this last couple of years, so I don't know if the IEEE committee has shall we say, recanted. Their point of view was they didn't care beyond scaling, but beyond about 20 machines. Which was beyond that is out of scope, as if you can limit how many people are going to walk into a big conference room and sit down, or into a school and sit down, right? Which can be hundreds. So, designed by committee, well, you know, I think a lot of the funny statements about committees are true. So, if too many of our machines could hear each other, we're too many of order 20 trying to run the mesh code. Everybody would be trying to talk at once. It's like the old Aloha net. Except it was so bad when we finally began to understand what was happening. You'd look at a spectrum analyzer of the 802.11 spectrum, and you'd see a shape that matched what you would expect on the channel you would expect, except all the structure was gone. You usually see some little fine structure in a spectrum analyzer, just plain gone. And we finally looked at it. We never saw more than about 14 bits before one of the machines would try to step on the other. Complete meltdown.
What happened about collision avoidance? Especially in a room of people, the other systems should become quiet if they get power in their inputs.
They weren't even able to hear enough to know that they should not speak. Okay? Because everybody would try to talk at once.
Jim, sorry, to say one thing. For example, wireless networks, classical AP networks, work very well when you turn down the power, like write meetings with like thousands of people.
Fine. But among other things, this wouldn't let us adjust the power. Okay, so if you have a school of 50 or 100 kids, you're guaranteed to have problems. Okay? So, there are lots of things that you might be able to do.
Right. Okay.
We weren't necessarily able to take all of these. Okay? Right? So I'm trying to say what the problems are. I'm not saying that these are necessarily insurmountable. Okay? It's just that here's a landmine, don't step on it. Think. Okay? I don't want you to make the same mistakes we made. I want you to make different mistakes. Make your own mistakes. Yeah? And so, yes, there can be lots of things like that which you can do to help, but they aren't necessarily always available to people. So this was one of the two major problems. We have a lot of other problems. So we had anticipated another problem is, as you know, is wireless not equal to Ethernet, even though a lot of people sort of think it is. It's not. So for example, anytime you send out a packet for multicast, at least with most access points, they tell, the reality is it drops things to the basic rate. So it doesn't take very much multicast packets, traffic, to saturate your network. So it's not the same. There are other interesting problems. Some of this we sort of understood in advance. So for example, we always presumed that in the school that it would probably be a bad idea to try to run multicast transport for these sort of reasons. So the collaboration software, actually, we did two different implementations. One of which was strictly multicast based, that would be used for a tree. And then if you're at a school, there'd be a school server where you might have something which you'd be talking to via unicast. And so we had a number of real problems. So we still had real problems scaling. So in this solution, we had a number of interesting headaches. One of which was, again, bandwidth usage. We were doing dumb things like transmitting keys and protocols that we built rather than when a key signature would have been fine, which meant that each of these packets were 5 or 10 times bigger than they needed to be. Okay? There were other problems. The Jabber server we happened to choose, and in particular with that Jabber server and how the what we had details of how the collaboration stuff had been designed caused at least that Jabber server to exhibit n-squared memory usage. Okay. Yeah, so again, at that point we could get up to of order 50.
Can you name any names?
Which Jabber server was that?
I guess the one in
Alarm?
yeah, it's the one in Erlangen.
Yeah,
Yeah, and understand that it was partly, and one of the real problems with that, as far as I was concerned, was there aren't enough Erlang programmers in the world. So you have a problem, how do you get it fixed? How do you even work on it? But part of this was driven by, since we hadn't thought through things from very low levels all the way to the top, some of the things we were asking the system to do could have been avoided had we actually been thinking more deeply from top to bottom in the system, and would have made it much easier on things like the server, but we only understood that later. Okay? So, okay, we figured some of this stuff out. We were able to scale things up to of order 50 machines. And we were still having lots of problems when we start to really use this stuff. I could never figure it out. So what was happening was, our collaboration software, our software would work on the network, and up to a point, then things would tend to slow down. Daddy the Internet today is slow today phenomena that I now know all too well. And start failing, where we'd see random failures with timeouts and things like the underlying protocols, and we could never figure out our things. I believe now, very strongly, though I haven't fully been able to get people to do this, but I know from all the other work I've been doing that buffer bloat can trivially cause multiple seconds of delay in things, and the transmit queue length on the OLPC is indeed set at 1,000. Okay, that's 1,000 packets of buffering, and particularly at 10 megabits per second of transport, you could figure out how long it takes to transmit 1,000 packets. That's how much latency will go into it whenever the network gets saturated. So this whole, it just doesn't, it keeps breaking. We can't understand it phenomena we were suffering from. I now believe with utmost confidence was caused by buffer bloat. Okay? If you put these horrible latencies into everything by having these huge buffers, there are real consequences only when the network starts to saturate. So everything starts taking way too long. You aren't ever pushing the endpoints to slow down. Yeah.
But don't you expect that in this situation, when you have a wireless mesh network that's saturated, you are going to have massive...
This is on a conventional access point. We were still having failures. This wasn't, the mesh is out of this equation now.
Yes, but you are having packet loss, so the TCP window shouldn't grow.
It doesn't grow as badly, but the whole aggregate behavior of the network just gets very bad. I mean, yes, part of what makes this hard is that if you saw the ragged 802.11 packet trace I showed last night from my in-laws' house, that the packet loss, if you get enough of it, starts being, you get multiple packet loss, TCP starts to interpret it as congestion and does slow down. But in that, as you saw in that plot, that still ended up at a 400 millisecond thing. Probably they'd adjusted the transmit queue to something more than infinity, more than less than the default, right? So there's a bunch of things I learned out of all of this, and I hope you can too. And the first point, of course, people in this room, I think, appreciate it better than most places, which is if you have some piece of your system you can't go look at and read the code when you have a problem, it's a lot harder to debug it. We know this. I really never want to go there again myself. Presuming that wireless is the same as an Ethernet is plain wrong. Presuming that a mesh is going to behave the same as wireless is wrong. And that a dense mesh is a fundamentally different beast than a sparse one. Okay? Net result of all of this is, if you naively believe, as we certainly did, that protocols designed and implemented basically with presumptions of an Ethernet are going to work in these environments under load at scale, you're going to learn the hard way. Maybe you won't learn. You won't be able to figure it out. I wasn't able to figure it out. Okay? I'm telling you flat out, we never figured out the buffer bloat problem several years ago, as we could not make our system scale. Okay? We never figured it out. So this presumption is really naive. You actually have to think. Dangerous concept. And this thing left over from OSI networking of layer 1, 2, 3, 4, etc. It's a nice shorthand for talking about networking, but so many engineers have taken this to mean that they don't have to really understand anything about how things above them or below them work. That's fundamentally incorrect. There is some networking 101 that everyone who does networking should understand, including basic things like congestion avoidance and TCP. Right now, unfortunately, most of the people designing our firmware and software don't understand that. Another piece of this, which I think this audience more than many understands, is that testing for scaling is hard. It's a lot of work to go out and set things up. And so one of my biggest fears now in how do we get buffer bloat fixed is yes, finding algorithms that may work may be somewhat of a challenge, but testing them at scale until we get something that just works, because red doesn't work. Doesn't just work, I should say. It works in some circumstances, but not the circumstances that people here care about. That testing is going to, in fact, I think, be the big challenge we face with the problem. And, so I'm in the boat. I mean, many of you are still trying to get your head around buffer bloat in the first place. I've been there. I've gone down in flames, just like many other people have. People say, our network has got 6-second latencies and don't understand it. I've been there and done that and never figured it out myself. Only reason why I figured it out is I happened to luck into very simple circumstances initially, and when I got the trace, I knew how to take a packet trace, and I happened to know the right people and ask them, what's happening here? And unfortunately, I'd seen enough other problems. I kept pulling on the string, and it kept coming and coming and coming. Okay? So, happy to take all sorts of questions. Again, if you don't understand about buffer bloat, that's way more important than this talk. Okay? That's where you can understand it. Lots of it here. There will be much more over the next 6 months or a year out there as well. For example, the ACM is planning ACMQ is working on a case study for this, where we'll get together a bunch of interesting papers examining different aspects of this general phenomena, that sort of thing. I'm in Europe at the moment because in 10 days I'm talking at the transport area of the IETF to show them what I showed everybody here last night. That was my first run through of my IETF talk that you all saw for the transport area of the IETF, because the reality is that even the transport area of the IETF doesn't understand this stuff properly and what a situation we're in. So, happy to take questions on buffer bloat or on what we learned from OLPC, or didn't learn until later. That's where you can find stuff. Yeah?
What will be the test you would like to do on the network we just deployed?
Well, you have to test things under load. Okay? So we actually set up to do that at OLPC, set up test beds to try to understand and debug what we were seeing. And that's how we figured out things like the routing wasn't scaling and stuff like that. But the buffer bloat piece was subtle enough, trying to understand what's happening in the whole network, that we completely missed it. Okay? And we were trying to figure out, after all of this, why can't we make debug our software so it doesn't just time out and fail? Okay? When I've seen, in some of my experiments on my cable modem, I've seen things like DNS lookup failure. Okay? When I saturate my link, it causes all sorts of weird problems. Okay, it's causing, in my simple test, it's causing bursts of packet drops. If they happen to step on your DNS lookup, you could end up with bigger timeouts, things like that. And it causes all sorts of bad problems and subtle problems. And many protocols time out if they, so if your DNS lookup, it's going to try to do retries, but if it misses too many retries, however long the trial takes, if you then multiply by 3 or 4 of them in a row, you can exceed the timeouts, and then a failure is reported. Of course, often the people time out first. So when the latency gets bad, we're shedding load by people getting bored and going and doing something else, just because the latency has gotten long.
So is there a concrete, an actual test you suggest that we make tonight when our meshes are deployed? Show us in our mesh. We want to see it.
Yeah. But when we need to fine tune and test and look.
Well, what I didn't say in my talk for the IETF is, which is in my longest talk, which is online. Let me get it up on the screen, and I'll tell you what my test was. Oops, what just happened to me? Somehow I made the wrong thing happen. So, for a long talk, which is online with audio, with edited audio, with all the slides, and me talking way too fast. I managed to say it in 1 hour, but I don't expect non-native speakers of English to have much of a chance at the rate that I was talking. So what I did that my smoking gun was this, believe it or not, a one-liner, 2 commands. Is that simple enough for you? At least for the cable case.
iPerf instead of SCP.
I don't care. I was just using SCP.
iPerf can be very hard on the CPU on the server. You do it from multiple clients. That's one
You want to make sure you use whatever tool you use. You need to saturate the link.
But then what do we monitor? What do we...
The latency.
Latency. Only
On latency. So I'm pinging. Okay, here I am at home. All I have is a cable modem. My laptop plugged directly into the cable modem. So the CMTS. There were exactly 5 routers in the middle, if I remember correctly. Okay, one of which is the MIT border router. This is the local Comcast network in the Boston area. Okay, and my machine is in the Colo Center at MIT. So it's got a gigabit into the MIT border router that peers with Comcast. Okay, so I know I'm saturating the link. And so this, when it's unloaded, is a 10 millisecond path. Okay, that's the cable technology. It ought to be a lot less than that. That's what cable does to you. Okay, it's a 10 millisecond path. It's 25 miles, or it's about 40 kilometers. But it's, the cable technology is slowing things down. When I did my first test, my latency went up to 1.2 seconds approximately. Okay, and watching smoke ping. So this was my smoking gun, as I call it, in homage to the wonderful tool smoke ping, which if you don't know about, you should be running routinely to watch your networks. And so it was just watching my home machine, and I let it run all one afternoon while I was rsyncing the old X Consortium archives from my house to MIT, and this is what happened. This is 1.2 seconds, but also notice relatively high packet loss and huge variability reported by ping. The only times that these little windows when things are reasonable are only because it was so painful to try to surf the web and or read email that I needed to get some things done. So I suspended it a couple times during this multiple hour period. This is me doing one rsync. Okay? I can do it just as well with just one SCP. So that's what it did. And as I was saying last night, what I noticed initially, once I got the packet captured, and remember, this is a very simple case. This is as clean as it ever gets. When you see it in an aggregate network, you're seeing a way more complicated phenomena because there are lots of people injecting packets. Okay? What I showed is just even one TCP connection will cause buffer, the buffer at your bottleneck to happen. But you can have this aggregated across a whole network of machines. And then, as we've seen with 3G networks, you may see 5-second latencies and the like. There's buffer bloat in the 3G networks. Okay? Actually, Dave Reed has observed up to 30-second latencies in 3G networks. So in those situations, it's way harder to understand. You have to go really look at the packet traces, everything else. But now that I've confirmed in various ways that we know this is happening in 3G networks. This is not, it happens anytime in a single 802.11 network shared among a pile of people. You can have aggregate behavior there too, because there's many, many buffers. In that case, there's obviously too much buffer in the router, but it also turned out to be in the laptops. Okay? So what I first noticed was actually just looking at Wireshark, I had these horrible bursts of these black lines staring at me in the face. So I plotted them up with XPlot. This is what a normal TCP might expect to look like. Okay, nominal, if you look at TCP trace for what a sample, vanilla, simple TCP transfer might look like this. And instead, what I got on my cable was this. tilt. And these bursts, by the way, these are minutes here. Okay? These are minutes. So these bursts are like 10 seconds or so apart. Okay? TCP should never behave this way. It only behaves this way if you put these huge buffers in. You can do the same test with UDP. This is not specific to TCP. The only thing about TCP here is I happen to show that even one TCP connection on any modern operating system, which leaves Windows XP out of it, can also produce buffer bloat. If you have bursts of UDP traffic, you're still going to do the same thing. If you don't signal the endpoints to slow down, you're going to keep filling those buffers. Okay? So I saw this, and this looked like no TCP trace I could remember from working on HTTP in the 1990s. And so I did the, I saw a very similar trace on Fios, and then on wireless and Fios it looked vaguely similar. But again, the latencies were way higher than it should be for this path. And so I said, what the hell is going on? And so I went and talked to the experts. Okay? We've looked at this really carefully. Van actually says, and I don't unfortunately it's typical Van, getting things from Van Jacobson is always hard. He's never been good about publishing things. That since both ends of my particular thing were Linux, or my simple test was Linux, there was actually even, because Linux turns on the timestamp, the IP timestamp option by default, there's even timestamps in the data, in the traces I took, that proves the point. So there's no question here. So what is happening here, in what I did, we have defeated congestion avoidance. All these nice words you may have read about congestion avoidance, these buffers have destroyed it. It's gone, guys. And we have to fix it. Okay? We have to fix it now. And I wish I weren't wrong, but unfortunately it is. So.
But regarding mesh, okay, there is this issue of buffer bloat, but I have a couple of questions.
Mesh just makes it worse because every hop may have more buffering. So it multiplies by n, where n is the number of hops.
It's a more difficult situation, and it hasn't been designed for that. That's true. But first of all, what kind of routing protocol have you been using?
AODP.
I don't know what OLPC is. I don't think they've had time to.
It's a variant of AODP what 802.11s is using.
Yeah, well,
Radio via AODP. So
it's probably not the best choice.
No, it's not.
To start with. And have you been using RTS, CTS mechanism?
802.11s, I think, has some crazy stuff of its own, because it's only...
They have their own version of RTS.
They were using an early draft too.
Yeah, in addition.
I don't know. Understand what I said applies to what got implemented for OLPC.
Well,
what the standard, if it ever appears, actually does may be a different discussion. I sure hope they learned, but they weren't very different when I was doing it.
I was talking with Mikalis, who is like in charge of the wireless mesh implementation of OLPC, and like I've been putting lots of talks with him, lots of time with him, and essentially as you mentioned already, it was one side was a closed source driver from Marvell, so if there were
the firmware, we couldn't work out.
There were quite a few bugs in there, according to Mikalis.
Yeah, we had, and just getting it debugged was so hard.
Yeah, and
on USB to make it even harder. Because USB is broken, so you have brokenness. You have to talk to a broken bus to talk to bugs and broken firmware.
Right. And the second part, the second part of what he said back then was essentially like following the IEEE 802.11s standard procedure. He got the feeling that some companies in there, like I won't name any now, are interested into keeping a half-broken implementation of or a half-broken standard, so that they have their own custom improvements to make it actually work. Yeah. So this
that could very well be. I was not involved in talking to the standards people.
Right. This fits to your observation of, you know, design by committee can be strange.
Yes, it can be very strange, and there are times when people in committees have ulterior motives like that, where they'll do things like sort of want a broken thing to be the default thing in the standard, but make sure that you can do something else which might actually function.
Yep.
I don't know whether those politics were at play, but to begin with, they were. The reason why I'm so vehement about the design by committee here being so broken is that the presumption that you don't have to worry about scaling beyond of order 20 machines was insane to begin with. Look how many people are in this room. We just sat down together. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I won't count them all, but we're up around 35. And this is not a very big room.
Well, we have been
But
running
they have a
measurement
different model of they have a different model of deployment. They are seeing that access points mesh, while the clients are using.
Doesn't matter, but you can't stop people from sitting down together or putting the access points too close together.
Well, we have been
There were broken premises
Yeah,
in
but
this.
there is
We
a
have
system
been-
to their methods.
We have been running measurement with 600 nodes 5 years ago.
No, the problem comes when they can all hear each other in the 11S. It's when you've got too many where the radios can hear each other, they start interacting. When you have a sparse mesh, yeah, you can make this work much
But
better.
the mesh on OLPC is working on the 3 channels. You make 3 mesh.
So you make 3
1,
meshes,
6,
but that's
11.
3 times 20, and you got 60, and any school's going to usually exceeds that size.
There,
And
there's
so
a mechanism to.
but you can't. And so the teachers decide to take a larger class out under a tree one day, and it'll melt. You can't design things like that and have them work robustly. So the very premise that they could control a deployment like that is fallacious to start. And I've seen another instance like that I can't go into before. So there are people who just presume that, oh, well, it'll never happen. And the reality is things can happen. And in our case, we found to our disgust that they did happen. And happened at a nasty scale. So yeah, often, I guess the moral here is, yeah, you often will get things to work fine in a lab with 5 or 10. And as you guys know, when you actually do them in scale, 50 is different than scale 5, and 500 is yet more challenges. 5,000 is another set of challenges that keep appearing. And that's the classic sort of thing. So.
I interrupted you earlier, Electron. You wanted to say something, I interrupted you.
Well, when I saw or heard about 802.11s, I thought this will never fly.
Yeah, I think you're right. It didn't fly.
It's like people that were completely clueless said, "Oh no, let's make a standard."
Yeah. So Michaelis was clueless to try to use it, and I was clueless by not spending more of my time poking into it. So I lack clues too.
I think that the good thing is like that you know, there is a bridge now that you're here. OLPC is, you know, thinking about like, you know, talking more to the wireless community folks in Europe, as far as I know from the mailing list. So, I mean, why not use the opportunity? There's still 2 million or so whatever OLPCs out there.
Right. Unfortunately, the original vision of the autonomous mesh, where you could power the machine off, that's going to be really tough to do because there's no way to redo the firmware that's running out there properly because the spec's closed. It's one part of the OLPC that you can't really mesh with. And so while you can make your mesh work properly by doing it all in the Linux host side, you can't do what we wanted to do, which is make it fully autonomous in the module,
Which is a
great thing to want to do, right? So that's the pain.
You know, the crazy thing is that AODV, so many people I know have tested it. It's you're happy if you get any packages through it.
No, it sort of works at scale 10 or 15, and then it's n squared. You have fundamental n squared in a dense environment, so you plot the result.
Electra. Just one thing: the AODV they do in 802.11s use a signal-based strength metric. So it's not just a pure ALDD with hop count, which totally does not work in radio environments. So they do some tricks to make it work in really small groups.
Right,
At least that's what I think one of the early drafts got out into the open. But
okay, sure. I have one final question. Is the firmware at least working now
it works.
for basic 802.11?
Oh yeah, oh yeah. I mean, there's a child here who has an OLPC. It works fine. Unfortunately, there isn't quite enough RAM in the module to make it able to run both access point mode and the mesh stuff, which is
just another question. Would it, when I hear half a watt, would it be possible when someone designs a next generation OLPC, just to say instead of using some kind of firmware module, you just take the smallest router chip, run a standard Linux on it, just connect one wireless LAN chip to it, maybe an embedded one, and say you have two computers, because then you don't need this crazy firmware stuff. You have a huge part of the computer goes.
Well, remember we had this USB out there, so part of the problem is that USB sucks power when it's powered up. So these days, there is a version of that chip, the later Libertas thing, which I believe has an SDIO interface.
Just connected with Ethernet and internally if necessary.
Yeah, so there are probably better things you could do. At the time we were building that machine, the only thing we had in common was USB. We never wanted to use a device connected via USB at all. USB sucks.
Maybe really someone looked at the wrong tools at this. At the time the OLPC was constructed, there were lots of small embedded routers that might have been, with a little bit additional development, get a very small power consumption. Just a generic chip instead of a firmware by a special company.
So, I mean, basically, in some ways, the OLPC was an attempt to do something that was technologically 2 years ahead of what we could get parts for. There are problems, right? There are compromises. We knew that going into it. It helped change the industry and get the price points down. So I don't consider it a failure, just not the success we had hoped it could be, right? And there's lots of politics involved in that I'll spare you too about, including lots of interesting vendor politics too. But I'll spare you all of that in a public forum like this.
So the actual test we should do on the network here is to load the network.
And load the network and be observing your latencies and compute from first principles what latencies you should expect. So that's why when I started at 10 milliseconds on my path and it went to 1.2 seconds, IP networks running TCP should never have that behavior. From first principles, there should only be a packet or so waiting at that bottleneck. So adding the latency should only have gone up a millisecond or two, maybe, for that one packet. Instead, they went up to a second. 1,000 times the increment of latency than I could do from first principles of how the network ought to behave. So when I got this simple-minded SCP test, I looked at this and said, there's no way TCP should ever be working like this. Okay, what's happening with a 1 second latency appearing? When unloaded, I'm at 10 milliseconds. And when you look at the TCP traces, you see the TCP windows going huge. Okay, because it's never signaling with packet drop to slow down. So the window gets to be humongous, bloated. The buffers bloat what TCP does. And then, of course, eventually things fill and bad things happen. When they do, you finally slow down again, and the cycle repeats. Yeah, it's much more complex when you're in an aggregate situation. Yeah, so the first person I know who recognized that bad things were happening in aggregated stuff is Dave Reed, who reported on the end-to-end mailing list things that he should never see going on in a year and a half ago on 3G networks that he was testing. He was not seeing packet loss, but he was seeing high latency.
But that's also what Nagel reports in 1983.
Yes.
So
yes.
It's something that people have been looking at and staring and not believing.
Yes, and you must believe Nagel is right. I have just written there's a column that Vint Cerf normally writes for IEEE Internet Computing, and not the issue that just issued like yesterday or today, but the one that will be out in 2 months. Vint asked me to write his usual column about buffer bloat, okay? To help wake people up about it. I hope that it will go online sometime next week, but I don't have that confirmed for it. And so guess what? I point a reference to Nagel's 1983 RFC about this. Did you know that if you try to make a network lossless like this, things go to infinity and the actual throughput goes to 0 in the absolute case? That's what Nagel proved in 1983. Go read the RFC. It's wonderful stuff. In a few pages, he convinces you that you don't understand packet networks the way you thought. So 0 for packet loss. Since we don't have ECN deployed, this is a true statement. A network which has 0 packet loss all the time is, if it's any sort of a complex network, is either you're never saturating it or it's plain broken. Some packet loss is necessary for transport protocols to work correctly. And that packet loss must be timely. It can't be delayed by seconds or hundreds of milliseconds, many times the natural round trip time.
So your solution is to reduce the buffer sizes and drop more packets?
Well, this has been researched in huge degree over the 1980s and 1990s, and an algorithm called RED is widely deployed. If you go read my blog, you'll see why it isn't universally turned on. And it also turns out that that algorithm RED is not going to work in most of the wireless environments we face. And that's talking directly with Van Jacobson, who with Sally Floyd invented RED. He said, don't try to go there. It's not going to work. We must use other algorithms. Unfortunately, he tried to publish the a paper to explain this to people twice and failed.
So there is an algorithm, but it's not working correctly?
There are 2 or 3 candidate algorithms that we need to test, okay, for managing buffers that we know of at the moment. Maybe it'll be more invented. Julius has implemented a thing called SFB, Stochastic Fair Blue, which is one. There's an algorithm that has just gotten implemented in Linux. You can actually, the kernel I'm running here is running it. Done by some folks at university in Ireland, whose name I need to go look up.
What's the name of the...
Do you remember?
Is that true?
No. This is the... It's not going to be suitable for routers. This is the... I don't think. In any case, and then Van has an algorithm which has never seen the light of day that may be another contender, and I haven't looked at chokes. We have 3 or 4 possibilities that might work, but we haven't tested them.
All of those algorithms have names of colors, because Van Jacobson started with red.
Right.
So just pick a color and you get an algorithm. And you have plenty of fascinating papers.
Right.
So you have for 2-3
So the
years
first I'm
just
looking at
reading
black.
papers. Then there's black, there is purple, there is
Yeah.
blue, there
Well, and there's more than 100 papers just about tuning red. Okay? Just about tuning red, which says it's got problems, guys. If you can't figure out how to do this easily, there's a real problem with red.
If I may add something to the subject, so
Yeah.
those are router-based algorithms, and you also have an endpoint-based algorithm.
Right.
which consist in sending data less aggressively. But you have a problem with those, because if you are the only one being less aggressive,
You can never get to the point.
then you are being penalized for being nice.
And the probability of this working is, deploying is almost is
one
effectively
thing
infinitesimal.
that people have been speaking about is to penalize aggressive flows. So if the routers are not taking care of flows, they're just penalizing aggressive flows, you encourage people to implement less aggressive end-to-end solutions. And that is what SFB and what Choke are attempting to do,
Right.
to detect which flows are aggressive and to draw packets from these particular flows.
And I warn you that very good people have worked on this for a long time, and it's a non-trivial problem. So the issue, we can immediately do things to suffer a lot less just by, since a lot of these buffers are just insane numbers picked out of thin air as far as I can tell. So we can immediately at least cut them to something sane for the circumstance. The fact that right now Linux defaults to 1,000 on its transmit queue, whether you're running at 10 megabits a second or 1 megabit a second or 10 gigabits a second, might tell you there's something wrong here. So there's some very simple things we can do like that to suffer much less. And we can do that very quickly. But I do want to warn people that showing that we've really solved the problem is going to be non-trivial. Where we have some candidate ideas and algorithms, we need to test them very carefully in real networks at real scale before we can tell the world, we've solved the problem, now do this. Okay? So you know, that's the conundrum we're in. We have a balancing act. We can start suffering much less immediately, but to really say we've solved this problem so our latencies are where they could be all the time, that's harder. Any other questions, or are we done? I guess we're done. Nobody asked me for 10 seconds.